Hello friends, thus today I am going to discuss Euler numbers and how to apply the Euler numbers in Python programming language. So let's see the Euler numbers. So it's a Euler's number. So Euler numbers it's like this means one of the most important questions why Euler numbers is used so much. So Euler number it's a exponential functions and you can say that this function is derived to itself, which is convenient for exponential and logarithmic functions. So we have already discussed in the previous video like a part 1 exponential and logarithms and how do we write the algorithms in a Python way. So let's see, we try to learn here like a derivatives. Later we will discuss in this step topics. But so in the many applications where the base doesn't really matter, so we pick one that results in the simplest derivative and is a Euler number. So that is also why it is a default base in the many data science functions. So let's Euler numbers means you say we are taking a loan from a bank like $100 to the somebody of the 20% interest annually. Typically the interest will be compounded monthly. So interest each month would be like a 0.20 divided by 12 and it becomes the sum a specific value. So how much will the loan balance after 2 years? So according to the rules, just we have already learned from the basic mathematics. We can come up like a formula, calculate the interest, and it consists of a balance like a as a amount. So let's write a, this means amount, and p should be like a principal, and r should be like a rate of interest, and time durations we can write the like a n should be will equal to time, right? So how do we write the formula? It's a amount should be equal to, it's a principal, it multiply with the 1 plus r by like a, it's a, you can take the number of the month, so it's a number of the r by 100 and it's a n, it's like this. So it's a compound interest, and if you are writing as the monthly way, and if we can take like a m as the month, so it's a possible to the, if m is month, so you need to write a will equal to t and 1 plus r by, it should be m, r should be in the percentage term, and it's like this. So the loan would be grow like a according to this formula. So let's see, if we are talking about suppose $100 and we have $100, so we should write here it's a equal, so it's a 100 should be multiplied with the, it's a r in the percentage, so it's a 20% should I write here, 0.20. So we are talking about the like a 12 months, and we are going to got here 12 into 2 for the 12 2 months here. So and we will get a output. You we are now I am using a calculator, and it's a possible to we will get here like a it's a approx value this amount. But if I want to do this in Python. So let's do here. How do we do? So let's go the Python language. It's a yeah, right. So we should write here Euler and first we can import here calculating the compound interest in Python. So let's go calculating compound interest in Python. So let's see from math import exp from math import exp like exponential. Let's see here. So yeah, it has been imported, and now let's write the some basic. It's p should be like a principal. It should be equal to the 100, and now r should be equal to 0.20, and time durations its t should be equal to like a 2 years, and n should be equal to it's a 12. And now I want to write here PAA as a variable, so it's a will equal to P, and now the star should be multiplied with it's a parenthesis 1 and plus next parenthesis it's a R divided by N. It has been closed, and it should be a power like N into T. So N star and T here. Now print it. Print A. Let's see what happened, because we have created here, and it's a N T. So it's a 100.20 time durations we have taken as 2.0, N will equal to 12, and P should be multiplied 1 plus R by N and close this bracket, and it's a not a NT, we need to the put here inside of parenthesis. Now it's clear. So yeah, let's see your answer. It's similar like a previous. So if the compound interest is the daily, so what happened, then it's a change like a n to a n to 365. It's a, if you want to get a compound interest daily, so you need to change like a time duration is a different. So I think it should be like a enhance of the 12 we need to the right. If you want to the daily, it's a yearly, and if you want to a daily, so let's do here same process. Control C here. If we compounded interest daily, if we get compounded interest it's a daily, so we will change is the like a 365. And now look here, yeah, let's see here, it's a daily. So I think it's clear. So if we want a compound interest the every month, so we can, it's every month, so we are getting here that t will equal to 2 months, so we have gotten this one. So I hope it's clear. So how do we get the daily calculations, and how do we get like a monthly calculations? And similarly, if the compound our interest the daily instead of the monthly, so we would earn like a 47.46 cent more at the end of 2 years. If we got a greedy, and why not a compound every hours? So the next, so n should be changed like a 8760. So it's a possible to convert in the every hour is also. So we are only the gaining the small and smaller functions of a cent that more frequently we compound. So if we kept making this period infinitely smaller to the point of compounding continuously, where does this lead? So let's the introduce your Euler number like a E as a E, which is the approximately 2 point is value of the E will 2.71828. So here is the formula of the compound continuously. So if you are applying like a compound continuously, it's a compound continuously like a continuously. So then a should be equal to, so a it will equal to like a p into e to the power rt. So let's see, it's 100, it's equal to e to the power 0.20 into 2, and now let's get here 149.18. So this is not too the surprising the considering the compounding every minute got us and balance of the 149.18, so that got us really close to our value like a 149.18, so when compounding continuously. But how do we write like calculating the continuous interest in Python using exp functions? So let's go ahead. So let's see here, and now calculating continuous interest in Python. Continuous interest in Python. Like a from math import exp, from import exp, and now you write pr and t, it's a similar, and a should be equal to like a p exp rt, and print here t. That's this one. So we derive this constant and it's a continuously. So let's see here the continuous interest formula we can see here. So I think it's a clear and we can easily understand how do we get, and we can also like it converges approximately the sum value like e will equal to the 2.71. Next we try to discuss the natural logarithms. So what is the natural logarithms? Let's go here. Let's see the natural logarithms. Natural logarithms. So we can write like a log e10, it should be equal to like you can write ln log 10. So when we use e as our base for logarithms, this one we call the natural logarithms. Now depending on the platform, like we may use a ln instead of log. It's a instead of it's a log. To specify the natural logarithms, so rather than express a natural logarithm, express log e10, and to find the power raised on e to get 10, we would shorthand in log 10. So it's a log e10 should be equal to the log 10. So in the Python, a natural logarithms is specified by the log parenthesis functions. So let's see how do we write here. So now let's go, and now it's right here natural log. So e raised what the power give us 10. So from math input log, math input log, let's check it. Now we are assuming the variable x should be equal to log 10. So log 10 and printfs. So I have gotten a value like a 2.30. So we will use e in a number of places throughout from these algorithms. Similarly, let's means we are going to discuss here the limits. So what is the limits? First, I need to the erase. So after Euler numbers, I am going to describe here limits. So let's see. It's a limits. Limits, suppose just I have already discussed some formula like a fx, like a function should be equal to 1 by x. So take these functions, and now I want to plot these functions. So it's a easy, we can functions that forever the approach like a 0 but never reaches 0. So we are looking only the positive x. Notice the x forever the increase f gets a closer to the 0 and never actually reaches 0. It's just forever the keep getting closer. So how do we write like a therefore something like we can write here fx, it's a limit x tends to infinity, and we can write here 1 over x. It's a 1 over x. So let's see, if I write here limit x tends to infinity and 1 over x, it should be like a 0. So it will keep getting a closer to 0 but never reach 0. So the way we express a value that is forever being approached but never reaches it through the limit. So x approaches infinity like this. This is the pronounced like a x approaches, yeah, you can say, or x tends infinity. The functions 1 by x approaches 0, never reaches 0. So we will see this kind of approach but never touch behavior a lot. So especially when dive into derivatives and integrals. So Let's see how do we write with a simple. So see here, it's a, we are talking about like a limit, so we should write here limits, and now from im simply import x should be equal to symbols f will equal to 1 over x, result should be equal limit f x, and infinity we need to write here 0 0. It's not a 0 0, we should write like this and print result. It's a print result. So let's, I have got an output like a 0. So we discovered the Euler numbers e and this way too. So the result forever like a extending the n into infinity for these functions also. If I write this type of the functions with the limits, so let's see. Just I want to write here. It's a limit one functions limit n tends to infinity and 1 plus 1 over n is to the power equal to n. It should be like a e, and your value should be 2.7182 something. So let's see how do we get in a Python. So first we need to write here like a n, and let's see, just copy and paste. N should be equal to symbol 'n'. F should be equal to like a 1 by n, and now result should be this. It's not the capital N, it should be the small n. Let's see, it's a running and not running. Yeah, it's a working. and now we want to the get result should be limit it's a f and it's a 0 and print result. So let's see, just I have gotten a result here E, but I want to the evaluate. So let's see, I want to write here print dot e e v a l and sure. So I have gotten the output here 2.71. So let's see, try to understand what is the SIMPy and power of the SIMPy. So SIMPy is a powerful and fantastic computer algebra system, like you can say the CAS for Python, and that use exact symbolic computations rather than approximate computation using decimal. It help it's helpful for those situations when you would use a pencil and paper and to solve a math and calculus problem with the benefits of using a familiar Python syntax. So it's a let's do here. Next we are going to the describe like a derivatives. It's a derivative tells the slope of functions and it's useful to measure the rather of change at any point in the inner functions. So why do we care about like a derivatives? It's a important and it's used in a machine learning and other mathematical algorithms, especially with the gradient descents. And when the slopes is a zero, that means we are at the minimum and maximum of the output variable. And this concept will be useful later when we do linear regressions, logistic regressions, and neural networks. So let's see here. Now we are going to take a one example and we try to plot this example at this point. So it's a slope will equal to, we can say, the y2 minus y1 and divide by the x2 minus x1, and we try to show the derivative calculators implemented in a Python also. So let's see. Let's start with a simple example like if we have functions like fx will equal to x square, it's a quadratic functions. So let's see the whiteboard and I will erase first itself. It's a differentiations. Differentiations. So now the differentiations means derivatives. You can also say like a derivatives. So let's first I am taking like a fx. I have already discussed in the previous video. It's a quadratic functions. So let's see fx in how a step is the curve of x will equal to 2. So first question is how step is the curve at x should be equal to like a 2. It's a question. So we can measure the steepness at any point in the curve, and we can visualize this with a tangent line. So think of the tangent line is a straight line that just touches the curve at a given point. It also provides provides the slope at a given point. So we can estimate a tangent line at a given x value by creating a line intersecting the data x value and a really close neighbor's x value on the functions. So let x will equal to 2 nearby the your x, you are putting this value like a x, it becomes like a 2.1. It will be like if I am taking like x will equal to like a 2, so your function should be like a 2 square, it becomes a 4. Similarly, if you write here the 2.1, so it becomes like a 4.41 and so on. So the resulting the line passes through the 2 points has a slope of 4.1. Slope has like a 4.1. But we can like quickly calculate the slope of the m between the 2 points. So we have a 2 points like this and this. It's a x1 and it's a y1, and another is the like a x2 and it's a y2. This point is the a and this point is the b. If I want to get a slope of this line, so we can write here m will equal to y2 minus y1 x2 minus x1, right? So how do we get the slope here? So slope we will get here 4.41 minus y, it's a 4.0 divided by 2.1 minus 2.0. So it should be equal to 4.1 is your slope. So if we made the x steps between the 2 points even a smaller, like x is 2 and another is the x will equal to 2.0, which would be the result like a 4 and 4.0. Let's try to derive calculators in a Python. So it's derivatives in it's a derivative. So let's how do we derive? So we will write here the df derivatives, derivative underscore x. Just we have created these functions derivative underscore x. Now f comma x comma step underscore size. Now we write here m should be equal to f x plus step underscore size minus f. Now it's divided by x, it's a plus underscore size, and it's a minus x. And now I write here return m. So first derivative functions has been created and f, x and step size return, and now let's create the another functions like a def and my functions. No, it's a m, it's a go back div my underscore function return return slope underscore rate. So let's create the another variable slope underscore at the rate of 2 here. So 2 should be equal to derivatives underscore x my functions comma is 2 now comma it's a point, it's like this. And now I want to print here slope underscore at the rate of 2. Let's see what happened. So you could see here your output has been like this 4.00. So now it's a good it's a clear way to calculate the slope anywhere on the functions, and we will apply in the we do the practice in the number of times, and so it's a very easy way to understand the slope. Thank you very much. I will try to discuss in the next part like a partial derivatives and integration. It's a chain rule, then I will try to discuss like integrations. So thank you very much.